Okay, so last time we discussed how to construct the deformation scheme of an immersion. So let me start by reminding you of that. So what we did was X is a scheme. Well, I think the notation, let me follow the notation from last time. So Y is a scheme, X in Y is a closed subscheme. So then we consider the blow up. So I will define mxy as the blow up of y cross p1 at x cross well, infinity or 0, it doesn't matter. So last time I was just following the notation from Fulton, so I did it at infinity, but today I'll just write 0, it's fine. And then row from we have mxy to p1. So this is the map. So you basically blow down to y cross p1, and then you project to p1. Right? So then we saw that rho inverse of 0. This is equal to the union of the exceptional divisor E and y tilde. So here E is equal to exceptional divisor and E is isomorphic to the projectivization of Cxy plus 1. Okay, so Cxy is the normal cone of x in y, and 1 is the trivial line bundle over x, and this is basically the projective completion of the normal cone. And so actually so p of Cxy plus 1 contains a copy of contains a closed so it has a closed subscheme, isomorphic to the projectivization of the normal cone P of Cxy, and the complement of which is isomorphic to the normal cone itself. Okay, not the projectivization, the actual normal cone is sitting in there. So this is what we saw, and then y tilde, this is the strict transform of y cross 0. Right, so y cross 0 is the slice. You blow up x cross 0, and then you see what is the strict transform, and this is basically going to be isomorphic to the blow up of y at x. And so this blow up, in this blow up, the exceptional divisor is exactly this thing, right? So so y tilde intersected with E is exactly this PCXY. And so what we do is we define M. So this is something I didn't write last time, but I define, so I put a O up here. So this is equal to M xy minus y tilde. Okay, And so I will continue to denote this. If we continue. Denote, okay, maybe denote rho, the restriction of rho to M0xy by rho. And so rho, okay, maybe I shouldn't do that, but I'll do that later when I start using this. So notice that if I look at rho restricted to M0xy, and I take the inverse image of 0, that is that is C, that is isomorphic to Cxy, and everywhere else the fiber is looking like y, right? So this is how you get a you manage to deform the embedding of x into y to the embedding of x into the normal cone. Okay, so now what I want to do is, I want to, so the main theorem that I want to prove about this is as follows. So, as before, y is the scheme, x subscheme. Then what I do is, for any okay, what I will do is I will define a map. I'll define sigma from the k cycles of on y to the k cycles in Cxy. So we define this by sigma of, so for any k dimensional variety, what should we do? So the definition is sort of the only thing that would occur to you. You take the intersection of v with x, and then you take the cone of v at this this closed subvariety. Okay, so this is I mean, as I said, we are looking at the cone as a tubular neighborhood around x, right? So now the idea is just to intersect v with that neighborhood. So you just take the cone, and so the theorem is that then, so this so if so okay, one thing is that this is actually a homomorphism. If alpha, so this is a homomorphism, and well, actually, I define the homomorphism like that. I don't need to say that. This is how you do it for the generators. And then the point is that if alpha is rationally equivalent, if alpha in Zx, Zk, y is rationally equivalent to 0, then sigma of alpha is rationally equivalent to 0. And so we have a homomorphism sigma from a ky to ak of cxy. So when I prove this, I mean, I'm following Fulton's proof, so I'm not going to prove this exactly. I'm just going to define a morphism and define a homomorphism like this and check that this is how it behaves on these generators, right? So that is, so fortunately we have most of the machinery that we I think, yeah, we have all the machinery that we need for this. So proof. You have Cxy sitting in so this is sitting in M0xy. This is a closed embedding, In fact, this is actually a divisor, right? This is rho inverse of 0. So it's the pullback of 0 on P1. And you have the complement of this M0 Yx. This is isomorphic to Y cross E1. So now we, I think one of the last things that Nitin did today was the localization sequence, right? So that's what we will use now. So you have A k plus 1. So okay, I mean I could have written k, but anyway. So the reason is that will become clear once I write this out. So this I have C x y mapping into A of k plus 1 into M0 xy. This goes into A k plus 1 y cross A1 into 0. So this is an sorry, yeah, that's what I meant. Sorry, minus cxy. This complement is this. So this is, so I have this exact sequence. Maybe I should have write it a little better. So we have this exact sequence. So A k plus 1 cxy to k plus 1 0 xy. Okay, and now, so what are these maps? So let me call this one as I, and so J is the y cross A1 into 0 xy. This is open immersion. Right. So this map is I lower star, and this one is J upper star. Okay, now the thing is that we have a map going like this. So this is I upper star. So this is one of the things that Amit discussed, right? So the Gisin homomorphism for divisors. So I will write a little more about it. I mean, so but let's just say that this is the pullback along I, and so since the relative dimension is -1, so it actually goes down, right? So from AK plus 1 it goes to AK. So wait a minute, what am I saying? And then you have this map. So you have a map actually. Okay, how should I write this? I have the flat pullback from AKY to this. So this is going this way. So you take the projection and you take the flat pullback, and this is actually an isomorphism, right? This is also something we saw. Okay, so now let us comment a little bit on I lower star. See, Cxy is equal to rho inverse 0 is a divisor in M0 xy. So I upper star is the Gisin homomorphism for divisors. And how does this work? I upper star of any alpha, this is just going to be the intersection Cxy, so this divisor times alpha. right? We have seen how to take the intersection with divisors. So that's all this is. Well, what is this supposed to be? This is supposed to be equal to also, you take the Chern class of, if you, this is also like you're taking the Chern class of the normal bundle of this. So the normal bundle of Cxy into, okay, this is, yeah, maybe I'll write it more precisely. So this is, where is this sitting? This is sitting inside a k of Cxy, and the thing is that if I push this forward again, I lower star of Cxy dot alpha, this is the same as taking the Chern class of the normal bundle of Cxy and in y cross in m0 xy, right? And then cupping with this, cupping alpha with this, right? So to take the this intersection, so this is just definition, right? And taking the intersection with this divisor is the same thing as cupping with its Chern class. So the only reason why I'm writing I lower star here is so that because this is sitting in AKX in the Chow group of CXY, but I really want to see it as sitting in here, sitting over here. So I just push it forward again, right? So, but the thing is that what can we say about this normal bundle? So the normal bundle of Cxy on so the normal bundle of this at Cxy in m0 xy is the pullback of the normal bundle of 0 in P1, okay, along row, right? So this is just a row upper star of that normal bundle. So what does that tell us? So this normal bundle is trivial, right? So this bundle is trivial, and so what this tells us is that so where is the diagram? Yeah. So if I, this, so if I go like this, right? So I basically get 0. So so I upper star is the 0 homomorphism. Wait a minute, that doesn't, and so I'm a little bit worried. Was it entirely supposed to be? So I upper star, I lower star followed by I upper star is 0 homomorphism. Yeah, there's nothing wrong with this, right? I mean, if I take the intersection with a divisor with trivial with a trivial normal bundle, I should get, that's the 0 homomorphism. Okay, just okay. But what I really need is that this composition is the 0 homomorphism. So if this is the 0 homomorphism, then this map, okay, again I have there's something off about this. I lower star. Why is that 0? Oh, so sorry. Yeah, that is, I've written the wrong thing. I just meant I upper star. No, this is fine. This is fine. See, the idea of this was, I mean, I don't need to write this actually, right? I could just say this. The point was just to see it. Maybe I will not write it. So you understand that this is, I mean, it's just to adjust this, where I'm seeing this. So this is the zero homomorphism, and the point of this thing is that since this is an exact sequence, I should get a map I should get a homomorphism like this.
So this is, we defined this as pulling back the line bundle corresponding to Cx by 2 alpha, right? This Cx by dot alpha was that. Why is the normal bundle?
Why is the normal bundle trivial?
You have written at the bottom. So this was defined. So d dot alpha was defined as take the line bundle corresponding to d and pull it back to alpha. So,
yeah.
Could you explain why the normal bundle is of that thing?
Normal bundle is why it is trivial?
No. Why have you written this dot as? What is one of?
Yeah, wasn't this proved actually?
This was defined as take the line bundle corresponding to Cx and pull it back to alpha. Right?
Yeah.
So are you saying that the line bundle?
Yeah, this is this was defined as that. Yeah. See, I mean, then how is this actually? Isn't this actually also so? Taking the cupping with the churn class, isn't that also defined? Wasn't this defined like this? Also, yeah. Yeah.
I think you just in the previous lecture was done.
Yeah, I think this was done. Yeah.
As a part of that theorem about
No, actually, I'm a little bit concerned that I'm saying. Yeah, I think I'm saying something wrong here. It's just that I can't see the problem because see
because you have to check that the composition is zero, right?
Yeah, that is all I need. Actually, this must be off. There is something off about this.
Where are you starting with the alpha? Where is alpha?
Actually, I mean, I'm just talking about this alpha is. I'm just trying to understand this map.
But now you have to only focus on those alphas which come from the
Yes. No, but the question is that why? I mean, there is something wrong with my statement that I upper star is the zero homomorph. That statement has to be wrong, actually. Because otherwise, what is sigma? Then why would I bother defining sigma?
If we take the line bundle corresponding to CXY, that is trivial. So its restriction to any subdirecting is also trivial. That's why this is trivial, right? So if we take upper star, then I lower star, actually place subdirecting V of CXY. So this means that restriction the line bundle, because line bundle OCXY to the subdirecting. But CXY restricted to CXY makes it trivial. So restricting to subdirecting is also trivial.
No, I understand. So what you're saying is that this composition is zero. Yeah, that is fine. But I'm just saying that what I have written here has to be the wrong is not really right.
So you mean that I upper star on the whole is not the zero?
Yeah, it can't be right because. So I'm making.
So this line is right. I lower star, I upper star.
Yeah.
Is zero.
Yeah. That is true. Which one? This one?
By the way, why is that trivial? Why is you said it's a pullback of the normal bundle?
Yeah, it's basically. I mean, the picture is that this is the pre-image is the fiber over zero in this. Yeah, so anyway, I mean, maybe we'll come back and fix this, but right now the point is that this composition is zero. That's why I have a map like this. Yeah, we will have to fix this though. So we have a homomorphism. From the co-kernel of I lower stars from ak plus 1 of y plus a1 to c to ak of Cxy, which induces sigma from ak of y to ak of Cxy. Yeah, but I mean, so clearly this map cannot be 0. But yeah, the composition is
See, why is the even the bundle is trivial? Why should I have to start with the zero?
oh yeah. Oh, 1 second. Yeah, I've that
I
is
think
only on this. Yeah,
CXY.
yeah.
So the bundle is trivial on the point 0.
Hmm.
So put that to the pre-inverse of 0. The put that bundle will be trivial on pre-inverse of 0, which is
Yeah.
Cx. So this bundle is trivial on just the point.
Right. It's on, this is only happening on Cxy. That is true. Yeah, this is correct, and so yeah, this is also correct, and so so I think this is basically the point, right? I was star. Yeah, so you first restrict. Okay, so now you first restrict. Yeah, this bundle becomes trivial after you restrict, actually, right? That's, I mean, yeah, no, sorry, this. Yeah, I think this is fine. Actually, I'm just probably. Okay, I think what is written here is right now. Okay, I'm just more confused than I need to be. Maybe we'll talk about this again a little later if it needs to be clarified. But anyway, so now you have this homomorphism, and now let us understand what it is doing. So what is it doing to V? So what is sigma of V? Where V in Y is a k-dimensional subvariety. So P upper star. So sorry, the product, the pullback along the projection of V. This is equal to V cross A1, right? So this is just when I pull back, I've got V over here. When I go up here, I just get V cross A1. And then, so how do I construct this map? Basically, I take anything that is that maps to this, right? Pick anything over here that under J upper star maps to V cross A1, and then take its image over here. So, where? Yeah, sorry. Now J upper star of M V intersection X of V, this is equal to V cross V. Okay, so then I can just take the image of this under I upper star. So sigma of V, this is equal to I upper star of M V intersection X of V, right? So basically, I'm just pulling back the, I'm restricting the divisor Cxy to this subvariety, okay, which is equal to C V intersection X V, which is so yeah, so that's basically what we wanted to do. Okay.
That last line on the third board.
Yeah, sorry. Yeah.
is it available in this upper alpha? So when I assume that I upper alpha.
No, I upper star alpha acts. Yeah, really, what I should have done is.
Alpha is square, alpha is in MX not
See, yeah, there is nothing wrong with this statement. This is true. But now the thing is that what we do is we start with, now if we started with some beta in AK plus 1 of CXY, then you take, you use I lower star. So I lower star of beta is say alpha. Then you apply this. Okay. Okay. So this is what this is the specialization homomorphism, so what this is used for is it allows us to define the Gaussian homomorphism for regular embeddings. Well, actually, what do I want to say? Embeddings, yeah, regular embeddings. Yeah. Yeah, I think I need a smooth, right? I mean, the varieties need to be non-singular, right? Yeah, not just okay. So, so if so, the idea is that if I'm just okay. So if y and x. Okay, let me just write down the statement that I'm trying to make. Huh? Yeah. So if so, the point is that if y in x is such that CXY is a vector bundle, then I can apply I think one of the last things that Amit proved, which then the pullback so from AK of CXY to sorry, AKY. So this is CXY. This is an isomorphism. Yeah, sorry, x is sitting inside. So then, yeah, maybe I will call this okay, I. So then we define I star from A AK Y to A K minus dx to be the composition because the dimension of sorry, this should have been x, right? Yeah, this should have been x. So this is a vector bundle of this of rank. So this is going to a k minus d of y. So this is basically the inverse of this. So okay, so this is one situation where we are able to define the Gaussian homomorphism. So anyway, we will have to come back to this tomorrow, because there's one more thing that I want to say about it. Yeah, okay, maybe I will write it as so yeah, this should have been x.
Yeah, this should.
So, okay, so that's all I'll say about this homomorphism for now. Tomorrow maybe I will add a few more comments to this. Yeah, are there any questions about this? Okay, so yeah, anyway,
Why the Cartier division, is it the same as the IISER we defined that Gaussian homomorphism?
so yeah, so that should be the case. Yeah, maybe we can verify that during the discussion session. So that's a good question, right? So if I is actually just the inclusion of a divisor, then we should check that this is the same as the one that we had defined earlier. Okay, so now I want to talk about something else, which is Segre classes of cones. So we have talked about what are the Segre classes of vector bundles. So if E is a vector bundle on X, we defined Si. So V is a vector bundle of, say, of rank E plus 1, right? So then we defined Si of E so we defined this as an operator. So this is going from ak of E of X to k minus E of X, right? No, ak minus I of X, and we defined this as Si E cap alpha. This is equal to I should have labeled things. So let's say that P from the projectivization of C to the projectivization of E to X is the usual map. Then what I do is first I pull back alpha like this, right? So then what will happen is that this will now sit in a k plus E of E, right? So this is going to sit inside a k plus E of E. Then I basically intersect it with the Chern class of O1 as many times as I require to make the dimension drop. So A of O1. So I have to do this E plus I times, and then I push forward, right? So this is what we did. Then we also defined S of E equal to 1 plus S1 plus so this sum, and then we took the inverse of that, and that was well, not this, then, okay, you take that polynomial, and then you take the inverse of it. That's how we define Chern classes, right? That's one way to do it. But now the thing is that we could see if we could try to do this for an arbitrary cone. So, can we do this? When E is replaced by so I'm not trying to define Chern classes. I just want to define this. Okay, so can we do this? So what would be the first obstacle that will come up? Yeah, so this P need not be flat, right? So but P from PC to X may not be flat. So then what we do is we don't just take any arbitrary alpha, right? We will basically just take so we could say that instead of taking any arbitrary alpha, we will take the fundamental class of X. Okay, but still, I mean, you can't pull back, but then you can sort of say that the fundamental class of PC is an appropriate replacement, right? So what I could do is here, instead of P upper star alpha, I could just write the fundamental class of PC. Now the okay, so we try to define SIC cap X X by with P1C playing the role of P upper star of X. So I'm just writing this informally. There is no P upper star, right? I'm just so we would like to define S of C. So what is this? I'm not trying to define an operator. I'm trying to define just something sitting inside AKX. Okay, so just something sitting in here as S of C. This is equal to P lower star of the sum. So let's say I greater than equal to 0. So I will talk about this, why it's okay to say this. So C1 of O1 to the power I capped with P1C. Okay, so this is what we would like to do. So this is actually okay. It's possible, however, PC may be empty. So this is possible. So to avoid this situation, what we do is, see, the thing is that so we define. So empty meaning it's just empty. It's there is nothing there. So this could happen when the cone that you start with, in sufficiently high degrees, it becomes 0. Right? That could happen. Because the cone that you are taking here could be just about anything, right? I mean, the graded algebra could be using is anything. So if it is 0, then you have this kind of. Yeah. So yeah, I mean, I guess, for example, what if what if C is equal to X? Right. So then, so we define S of C. This is equal to summation. Okay, P lower star of summation I greater than equal to 0, C1 of O1 to the power I cap P C plus 1. And this actually doesn't, this is essentially the same as this if this is not empty. Okay, so I will just let us just see why. So P C plus 1 contains PC as the hyperplane at infinity. Okay, and C1 of O1 cap with P C plus 1. So this is just going to be equal to PC. So if whether I write C over here, I write C plus 1, it is just going to be it will just shift the sum, right? I changes, yes, but yeah, that's a good point. But now here let us see. Okay, where did I write that? Yeah. Here, see, the I is always E plus I, right? So what happens? I mean, here even if my I is equal to 0, I'm still starting with E. So if E is less than I, what happens? Sorry, I is yeah. If this thing over here is less than E, then what happens? Basically, the point is that it doesn't matter whether I start with I mean that I'm starting with, whether I'm starting with 0 or 1, because the initial terms are anyway going to be 0. So if PC is not empty, this is the same. Then S of C is actually equal to P lower star of summation C1 of O1 to the power I PC. So you can add more ones and it's not going to change anything. Okay. So I guess, I mean, if you wanted to, we could just actually write say that this is a sum over all integers. That would make it even simpler. But then we don't know what to say over here, right? That's the reason. Okay. Okay, that is the definition. Now let us check that this agrees with what we have defined for vector bundles. So proposition. So if E is a vector bundle, over X, then S of E, this is equal to CE inverse cap X. Okay, so this is what we would like to prove. So proof. So yeah, there is not. I mean, I have essentially said what needs to be said here. CE inverse cap X. This is equal to the summation of SI of E cap X for I greater than or equal to 0. See, I'm just taking, so CE is, so CE is equal to 1 plus C1E plus so on, and I just take the formal inverse.
So he's saying the left AC is what is just defined as the right is both.
No, is that okay? See, I mean, so when we see, we had, so how did we define CT of E? This was STE inverse, right? So you understood that as just the formal inverse. It sort of works the same way if you set T equal to 1, right? Because anyway, I mean, everything is the whole, I mean, these are all operators, but I mean, they're still graded, right? So it works the same way.
So here we extremely connected or something. Or any scheme, so suppose they on a connected component C is empty, on other connected component C
That is possible, yeah.
but then they won't be equal, right?
What will not be equal?
So suppose X is two connected components, so one connected component C is empty, over another connected component, if they have two factor bundle.
Yeah.
Then if PC is not empty, but
No. So the thing is that, yeah. So okay, if okay, maybe what I should have said here is that if the components of C are C1 up to say CR and PCI is not empty. Yeah, that's a good point. Not empty for any I.
components of C means what?
So I mean, C is basically C is a scheme, right? So I can talk about its components. Yeah, so that's an exercise. It's a simple exercise, but so yeah. So as an exercise, prove that if C is a cone, then its components are also cones. So yeah, yeah, I'm glad you brought this up because yeah, this is true only when this is true for all the components.
So the same problem is right.
No.
You have two connected components. One connected component is a right to factor bundle, another one it is empty. So components are
No. So I'm saying none of this is not empty for any I. Then I'm saying that you could just not use the one. Our definition is with the one, but you can skip that if none of the components, the projectivizations of all the components are non-empty. Okay, so yeah, so let us. So what we want to see is that this is the same as what we have got here. So let us write this out. So this is equal to. So I will label P is the projection from E plus 1 to X, and Q is the projection from PE to X. So then, so what can I say about so SI E cap X, this is equal to by definition this was Q lower star of C1 OP PE 1 to the power okay, I should say E is a vector bundle, so let's say the rank of E is equal to E plus 1. So then this is E plus I capped with TC. So now note that if J is less than E, then Q lower star of C1O PE1 of J. So I'm just writing out explicitly what I said earlier, that if this exponent here happens to be less than E, then what happens? right? Because I'm taking the summation from 0. So let's just check this capped with PE. So what can we say about this? So what is the dimension of this? So let's say that the dimension of X is equal to n. So this is, what is the dimension of this? This is n plus e. What is going to happen here? So every time you cap with the Chern class, the dimension drops by 1, right? So this is equal to 0, right? So this is in, because where is this? This is in A of n plus e minus j of x, right? So that's what is that? Yeah. So so the point is that C E inverse of x, this is actually the same as q lower star of summation I greater than or equal to 0 of C1 of O P E 1 Pi cap with PC PE, right? So this is and then this is exactly the same as the other expression as C1 of O P of E plus 1. So this Chern class you cap E plus 1. So again it's the same thing as before, that this will just give you the hyperplane at infinity, right? So this is equal to P. And the restriction of P of O P E plus 1 to this hyperplane, to the hyperplane of infinity, the hyperplane at infinity is actually O P E of 1. So you can just verify this. This is not that difficult. You just so you have to see how the embedding is. I mean, it's just you can just write down the surjection, and so it's very clear that this is happening. Okay, so and so this basically completes the from this the proof should follow. So I will So this is the same thing as C1 of O PE 1 I minus 1 capped with P. Okay, so that's so they are basically the same expression for vector bundles. Okay, so now let us examine a couple more properties of this. So yeah, so suppose since we just talked about components, so suppose, yeah, I should let me just record this, so maybe we can discuss this in the discussion session if needed. So if C is a cone show that components of C are also poles. Okay. Now suppose C has components C1 up to Ct, and let Mi be the geometric multiplicity of C at Ci. Okay, so then the claim is then S of C is equal to the summation of Mi S of Ci. Okay, so this is quite straightforward. So proof. See, the thing is that Ci, this is another place where it sort of helps that we are adding this +1, because Ci is open and dense in P Ci +1. Okay, and so if you take if I want to see the multiplicity of P C +1, if I want to so this is going to be a sum of P Ci +1 for with some coefficients, and what are the coefficients going to be? Basically, you just, to see what the coefficients are, you basically only need to look at the generic points of all the components, right? But the components are just the are these guys. Their generic points are the are basically the generic points of the Ci's, right? So this is just again Mi. And so, well, now you just take this and then you apply the formula, and then the result will follow. Yeah, so now you also have to use the fact that O1 of this restricts to the O1 of each of the components, and that is also there. Okay, is this okay? There is basically one example in Fulton which he has not explained in as much detail as I would like. So what I will do is I'll just say a few things about it, and I'll basically we will figure it out as an exercise. Okay, so here is what we need to do. So firstly, there's an exercise. So this is actually based on what was done in Amit's lecture. So let's say that X is is pure dimensional scheme. So all the components are the same dimension, and so of dimension n, and E is a rank R vector bundle. And let S be a regular section of E, and Z be the zero scheme of the zero scheme of E. Of S. So then what I want to show is then if I take the So you've seen that the churn classes vanish after the rank. So the claim is that CRE evaluated at the fundamental class of X, this is equal to Z. Okay. So yeah, one thing is that what is a regular section? So this is something I actually was confused about, but the main thing that you need is that, so this is of dimension, so this has dimension n minus r. So the point is that, okay, I mean, I suppose what this means is that if you take a trivialization, then this will actually correspond to R elements of the base scheme. R element functions over the base scheme, they should form a regular sequence. So that basically ensures that the zero scheme of S has the right dimension. Okay, so so let me just explain why this should be true. So you already know this for R equal to 1. Right? When R is equal to 1, you have a line bundle, and you're taking a section, and then so look at its zero scheme. That is basically going to be the churn class, the first churn class acting on the fundamental class of X. Now, if you want to prove this for R, for a higher R, what would you do? So have you seen a trick today that allows you to do that? Yeah, so you use the splitting principle, and then this should come from that. But yeah, I think it's a little bit tricky. I have not worked it out completely, but maybe we can talk about this in the discussion session. So I think this will be a good exercise. This is one thing. So observe that if E and F are vector bundles, over X, then S of E plus F, this is equal to S of E times S of F. Okay, so this is because this works for the total churn class, right? We have proved that. That's the Whitney sum thing. So just that should also give you a result for the inverses. Now the question is, does this work for cones? So exercise. So let C be a cone on X, and let E be a vector bundle. On X. Then prove that S of C is equal to well, yeah, I mean, I should S of E plus C. This is equal to C E inverse cap SC. Okay, so if one of them is a vector bundle, then this still works. Yeah, so let me explain why. I mean, what? So this is something that Fulton has worked out in an example, but he leaves out one crucial detail, which I think is we could think about. See, the thing is, CR of E. Yes. 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 Where R is the rank. Yeah. So the way to do this is that you look at P of E plus C, and let P be the map from the projection from this to this. So this is, again, this is something that I myself have not fully worked out, but I think this is doable. That see the what Fulton says without much comment is that there exists a section of P upper star E. So you pull back E to this projective cone and tensor it with O1. So there exists a section of this whose such that its zero scheme is PC. Okay, so now PC sits inside this as a closed subscheme. The point is that you can actually cut it out as the section of this vector bundle, and now you use this exercise. Okay, and then the whole thing just falls into place. After that, the calculation is very simple. But so this is what you need to understand, and this is basically a geometric insight. Now the thing is that this, if I take E to be the trivial line bundle, then this is something we have already done, right? We saw that P of 1 plus C contains PC as the hyperplane at infinity, right? That's basic. So now the thing is that if you take that and you replace the trivial line bundle by an arbitrary line bundle, that's a slightly jazzed up version of that, right? And then this is a further jazzed up version. So I think this should be quite doable. So I mean, my suggestion would be that maybe you try to verify this over a trivialization of the vector bundle and see if it glues together properly. I think it should happen. We'll talk about it. Now, what is all this in aid of? So, what we really want to do is to apply this to normal cones. So what we do is components of C are I don't think you would need that, but yeah, you could start by proving it for irreducible.
Class J. That will be three dimensional. So that will be zero scheme.
Oh, I see. Yeah, okay. You could take C to be irreducible. Take C to be irreducible. Okay, but yeah, I mean, I think the challenge there is to just see that it glues together. I think Zariski locally trivial, it should be easy to see. So, okay. So, definition. So, X is a closed subscheme of Y. Scheme Y. Then let's say that C, I define C to be the normal cone of Y at X. So we define the Segre class XY to be the Segre class of this cone S of C. Okay, so this is, I mean, it's a fairly obvious definition. Not, I mean, we are familiar with this. But now, if you recall, I mean, yeah, in the definition, we are basically taking this object, right, the projective completion of the cone. So it is quite natural to start think about the deformation scheme. The deformation scheme will come into this picture. So let me show you how. So here is a simple lemma. So let Y be pure dimensional. and y1 up to yr, these are the components of y, and xi, x is a closed subscheme, x a closed subscheme, y, xi equal to x intersection y. Now let mi equal to the multiplicity of y at yi. So then Sxy, this is equal to the summation of mi s xi yi. Okay, so the proof is as follows. See, what you have is y is equal to summation mi yi, right? That is what you have been given. Now from this it follows that y cross a1, y cross p1 is, or a1, whatever, so this is equal to summation mi yi cross p. Okay, so these are the multiplicities of for this collection of schemes also. Now if I blow up, it should still remain the same, right? So m x y, this is equal to summation mi of m xi yi. Okay, and now what I want to do is I want to take a divisor, right? So there is basically there is a morphism, flat morphism from this into maybe what I want to say is no, this is fine. So there is a flat morphism from this. No, maybe I don't need that. No, I don't need that. So I look at the exceptional divisor, not the slice over 0. I look at the exceptional divisor, and I want to restrict the exceptional divisor to each piece. Okay, then what happens is that P of Cxy plus 1. So I'm writing this as if it's obvious, but it's not actually. So summation mi of P C xi yi plus 1. Okay, so the thing is, so what we are saying is that I have a divisor and I restrict it to various components. Then the components that I get for the divisor, they have, the divisor has the same multiplicity over there, over those components, right? So this actually is where the pure dimensional part, the part of the hypothesis is required. I need this to be pure dimensional for this to work. This actually comes, this is something you have to verify. It's a small argument, but it's a small commutative algebra argument. So you can you can look it up in the appendix. There is a small argument about this kind of thing. So this is the idea here. So suppose I have got y prime, a morphism like this. Y prime to y is a morphism of pure dimensional schemes. And x in y is closed, and let me call this f, and f inverse of x is equal to say x prime, and g is the from x prime to x is the induced morphism. So basically the restriction of f to x prime, f to x prime. Okay, then if f is proper, then I can talk about the push forward, and y is irreducible, and say if f maps each component of y prime onto y, then the push forward of the Segre class is the Segre class downstairs with an appropriate multiplicity. So the degree of y prime over y. Okay. In particular, if f happens to be birational, then this just tells you that the push forward of the Segre class is again the Segre class downstairs. Okay, and we will actually, so one way this would be useful is that suppose you want to compute the Segre class of something, you blow it up, right? You blow up x, and then upstairs x becomes a divisor, and so then it becomes, then you get a nice formula for the Segre class. So that's also something we'll talk about. And finally, if f is flat, then also this behaves well. So that's what we will do. Okay, any questions? Okay, so let's stop for now.